Okay, don't forget to sign in with the QR code over there if you haven't done that already. Okay, we're good. Chick-fil-A on the car. It's a long lesson too. I won't have a voice by the end of it. Okay, so this week we're going to do things out of order as well. The 10:30 and 10:4 are what we're covering, but 10:4 was the longer lesson that had more math in it. So I made the video for the 10:30. You don't really need this for the 10:4, so I didn't give you all a heads up or anything there, but that's a really short video. I think it was like 15-ish minutes. So, but today's lesson together has a lot of stuff in it. So, but this is it for Province Stats. For those of you who are not liking this, our other two units are all on geometry. Okay. So what this means is that next week, when I see you all, will be our review day, and then I'll assign your test after that. So next week, your 2 lessons will be review and test. Yes. Do you have a Chromebook? You have to have a device with a camera on it. So if any of you are not able to get the respondents to work on your laptop, we can make arrangements for you to take it in the testing center. Okay. You can just take it in person there. So for your exam for next week. Okay, so we are looking at measures of central tendency and variation today. So when we're through with this lesson, you're going to be able to understand and explain central tendency and variation, which just tells us our spread in the data. You're going to be able to compute the mean, median, and mode of a data set, and then find appropriate measures of central tendency. We'll look at measures of spread, and then a graph called a box plot, and comparing sets of data with box plot. We'll look at variance and standard deviation, and then normal distribution and percentiles. So 2 important aspects of data are its center and its spread. The mean and median are measures of central tendency that describe where the data are centered. The range, the interquartile range, the variance, the mean absolute deviation, and the standard deviation describe the spread of the data, and they are what we call measures of central tendency. So let's get into what these highlighted words mean and look at how to find them. It's not wanting to move today. There we go. The number commonly used to characterize a set of data is the arithmetic mean, which is frequently called the average or just the mean. The arithmetic mean of the numbers x1, x2, x3, all the way to the end is denoted by this x with a line above it. Okay, that symbol is read x bar. And so our formula for mean, all this is describing is you're going to add all your numbers up and then divide by the number of numbers you have. So have y'all found mean or averages before? So that's typically how your grades are maybe figured. Sometimes they're weighted, but even within, like in our class, we have weights of basically 20% on everything. But it's when you're finding your homework average, you're adding all your homework grades together and dividing either the number of points or the number of assignments there. That's finding the mean. Okay, the mean of 5 is what we call the balance point, where the sum of the distances from the mean to the data points above the mean equals the sum of the distances from the mean to the data points below the mean. So when I look at that on this dot plot, when I look over to the right, I have the points 8 and 10. And over to the left, I have 4, 2 3s, and a 2. For this set of data, our mean is 5, and that's just because if I look to the right, my first point is 3 spaces above it. My second point is 5. Well, 3 plus 5 is 8. Okay. I can go over to the other side. I'm 1 distance away here. I'm 2 here. There's 2 of those. And then I'm 3 away here. If I add all of those up, I also end up with 8. So when you find the mean, you should have the same distances when you add up the sum of those on each side. The data itself is not necessarily centered about the mean, but the mean, the data is centered about the mean, but the mean is not necessarily in the set of data. So sometimes your mean might be one of the points, but as you can see in this example, 5 is not graphed. It's not part of our dot plot. Okay, so your mean may not be one of your points. Okay, so this example here just shows that we have 2 different data sets. So for my first data set, I have 2, 3, 3, 4, 8, and 10. If I were to find the mean of that, I would add them all together and divide by 6. That gives me the number 5. So this set of data points has a mean of 5. Over here, when I look at these data points, I have some negatives in there. It goes from -30 to 20. If I add all of those together and divide by 5, I also have a mean of 5. Okay, well, these sets of data points have the same mean, but they are very different sets of data. Do you see what I'm talking about here? Okay, this is just spread out from 2 to 10, but this is a widespread, or from -30 all the way up to +20. So while those 2 sets of data have the same mean, this one is way more spread out. Okay, so that's why we're going to be talking about not just the mean, but we're also, or the center, we're going to also be talking about the spread of the data too, because the data could look very different even though it may have the same mean. Okay, another way that you can measure the center is by something called the median. The median is the value that's exactly in the middle of an ordered set of numbers. Okay? Now, I remember this by thinking about the median in the road. So when you're driving down the road and you have a median, it's in the middle, right? Okay, well, that's exactly what this means. It's the middle number when you put your numbers in numerical order. So in order to find our median, we're going to arrange our numbers from least to greatest. And then if we have an odd number of numbers, your median is just the middle number. Okay, But then what happens if you have an even number of numbers? You don't have a middle number, do you? So what you're going to do there is you're going to take the two middle numbers and average those, and that'll be your median. So if I were to look at this data we had back here, I have 6 points. Okay, so there's not a middle number, so I'm going to take those two in the middle, the 3 and the 4, and I would add those together, divide by 2. That would mean my median would be 3.5. Okay. If I'm finding the median of just those numbers from 2 to 8, my median is just the number 3, the one right in the middle. A median is often reported with something called the interquartile range. That is a measure of the spread that shows where the middle 50% of the scores lie within the median in that range. Those two numbers together, the median and the interquartile range, they form a much better pair to describe the data rather than just the median alone. And we'll spend some more time talking about how to find that interquartile range here in a few minutes. Okay, then the mode. Okay, so when we're talking about data, we talk a lot about mean, median, and mode. So mean was the average, median was the number in the middle, now we've got mode. Mode is the set of data that's sometimes reported as a measure of central tendency, but a lot of times when it's reported in that form, it's frequently misused. So the mode is the number that appears most frequently. If there is one. Sometimes you don't have a number that repeats. And so if there's not one, then you don't really have a measure of central tendency there. So a lot of times mode is reported with categorical data. All right, in this example, we want to find the mean, median, and mode for this set of numbers. We have 60, 60, 70, 95, 95, and 100. So we'll say those are test scores. Those look reasonable for test scores. When we want to find the mean, that means average. So I'm going to add all 6 numbers together, and then what do I divide by? 6, because that's how many numbers I have there. So I would pull out my calculator, and I would type in 60 plus 60 plus 70 plus 95 plus 95 plus 100, and then I would divide by 6. So that's going to give you 480 divided by 6. So that tells me my mean is 80. Now, when you all are typing this in on your calculator, how many of you have a TI-84 or 83? Is that what most of you are using? Okay, don't forget, when you're typing in a long list of numbers, you're dividing the whole numerator by the denominator. So you probably need to put, if you want to do it all in one step, you need to put parentheses around the numbers you're adding together. And then divide by 6 like that. And what did I do wrong? Oh, I typed in 395. Oh, did I go that crazy? I can't talk and type on my calculator at the same time. There we go. Okay. You could also type it in, so hit enter there, 60 plus, again, I can't talk and type at the same time. Take that total and then divide by 8. Okay. But if I type it in without, all in one step without these parentheses, then it thinks that you are only dividing the 100 at the end by 6, not that whole numerator. So if I type it in that way, it's going to give me the wrong answer. Okay. But it'll be pretty obvious if you do, because is that our reasonable answer? No. Okay. Okay, then when you want to find the median, you're going to take the numbers and make sure they're arranged from smallest to largest, which we've already got it there, so we're good. We had 6 numbers this time, so I don't have a middle number. So this is where I need to take my 2 middle numbers and average those. So I'm going to take the 70 and 95. Once again, you'd put parentheses around those in your calculator and then divide by 2, and that means your median is 82.5. Okay, then next it asks for mode. Mode means the one that appears the most often. Do you have any numbers that repeat? Yeah, which ones? 60 and 95. So this one we call it bimodal because you have 2 numbers that are the mode, 60 and 95. Okay, you all try this one. See if you can find the mean and the median for that set of numbers. Okay, since this lesson's kind of long, this is going to be your group work. We'll need to try problem. Okay, so just so you know, it's just a long lesson. Okay, so pair up, get groups of 2 or 3 once you have your answer, and see if you have the same thing for the median and the mean. You did see it. Okay. Yeah. I got 82. It's 85. You got any more time to check? You get a mean of 81.1? Okay. Then for the median, you had to reorder your numbers. Since we had 10 numbers, we had to look at the two middle numbers, which are 80 and 85. And so take those two and average them. And so did you get a median of 82.5? Okay, so although the mean is the most commonly used average to describe a set of data, it may not always be the most appropriate choice. So in this example, suppose a company employs 20 people. The president of the company earns $200,000. The vice president earns $75,000. And then 18 part-time employees earn $10,000 each. Is the mean the best number to choose to represent the average salary for the company? Well, if you find the mean, you're going to take 200,000 plus 75,000, and then instead of listing 10,000 out 18 times, we just multiplied it by 18. Divide by 20, because there are 20 employees. That gives a mean salary of $22,750. Okay, in this case, that mean salary of $22,750 is not very representative because that's not really the average salary at all, right? Wouldn't you think it'd be more the 10,000? Okay, it's just the president and the vice president are skewing that number up by having their salaries in the median, in the average. So the median or the mode this time would be a better description of what the typical salary would be. And that's because that mean is affected by those extreme values. In most cases, the median is not going to be affected by extreme values on either end, since it's literally the value in the middle. Okay, suppose 9 students make the following scores on a test: 30, 35, 40, 40, 92, 92, 93, 98, 99. Okay, this time is the median the best average to represent this set of scores? Okay, well, if we look at the median, this time it's going to be 92 because that's our middle number. We have an odd number of scores this time since there are 9 students that took the test. Okay, but would you say that the average of these scores would be 92? Definitely not, because all of these lower scores, it's like they don't exist if you say the average is 92. Okay, so from that score, you might infer that the students all did very well if you say 92 is your average, but that's not a typical score. So in that case, the mean, which is 69, if you were to calculate that, that's going to be a more appropriate average of the scores. But also that 69 isn't the best description of the score because of the fact of the spread of the scores. So it looks like on this test, you literally had half the class that had no clue what they were doing and half the class that knew it very well. Okay, so this is an example of where the spread would be a good idea to know. We'll talk more about that here in a minute. All right, on this one, is the mode an appropriate average for the following test scores? Okay, well, what is your mode for this data? 98, is that a very good average? No, definitely not. So 98 is not representative of the set of data because of the large spread of scores. And even if you were to find the mean or the median, either one, those would both be much lower. Okay, so when we look at this set of data, going from 20, 22, all the way up to 35, we have 20 is our lowest number and 35 is the highest number. So we can describe the spread by looking at something called the range. The range is going to be the upper extreme minus the lower extreme, or the maximum minus the minimum. So for this set of data, our range would be 15. We have an even number of data points here. So if we wanted to find the median would be 26.5. I would take those two middle numbers and average those. Okay, we can also split the data in half and find the median of the lower half and the median of the upper half. So when I look at the lower half here from 20 to 26, okay, the median there is 22. We call that Q1. And then when I look at the upper half of the data, the median there is 28. We call that Q3. Okay, now we mentioned the interquartile range earlier. We're going to call that IQR, so we don't have to write out interquartile range all the time. Okay, this is a commonly used measure of spread, and it just means you're going to take Q3 minus Q1. So Q3, remember, is the median of the upper half of the data, and Q1 is the median of the lower half of the data. So my IQR for this set of data will be 6. So when the interquartile range is reported along with the median, now you know not only the middle of the data, but you also know how spread out the middle 50% of the data are. So this IQR tells us the spread for the middle 50% of our data. Now we can use these measures of spread to make something called a box plot. A box plot is also called a box and whisker plot. Did you ever make these in like elementary, middle school? Okay. This is a way to display data visually and draw informal conclusions. Box plots show only the visual representations of what's called the 5-number summary of the data. Okay, so I've written these in red. The 5 things that you're going to put in your box plot are median, upper quartile, which is your Q3, lower quartile, which is your Q1, and then the least value and the greatest value. So those are the 5 things that you will have in a box plot. So here are kind of listed in more of a visual. Your minimum, your Q1, your median, which is sometimes called your Q2, your Q3, and your maximum. So those are the 5 points you'll need to make your box plot. And if we're looking at the data that we were just talking about earlier on the previous slide, then this is what your box plot would look like. Okay, our minimum number is 20. Our Q1 was, what was it, 20 something, 22. Our Q2 was 26, our Q3 was 28, and our max is 35. So you would literally plot those points. And then once you have your points, In order to make the box, you use the Q1 and Q3 as the outside edges of your box. Then the line inside the box is just a vertical line through Q2. And then that's the box part. And then we said it was called box and whiskers because you make a whisker to the maximum and a whisker to the minimum. Any questions about how to make that? Okay, so in this example, what are the minimum and maximum values, the median and the lower and upper quartiles of the box below? Okay, so the first number that you see plotted here, see if I can get this pen to work, and it's not going to work. Okay, is here at 0. That 0 point represents what? The minimum. Good. The next point we see is here at 10. What would that 10 represent? Q1, which is your lower quartile. The next point we see is the 20. What does that represent? It's your median, that's your middle point, okay, on the graph. So it's also going to be the median or the middle of the data points. The next point that I see is here at what looks like 35. So what is that representing? Q3 or your upper quartile. And then this point all the way at the end is what? At your maximum. Okay? Okay, you all see if you can try this. Can you all read that okay? See if I turn these lights out. Any better? Not really? How does that help? Oh, I guess I can keep clicking on it and then it. Okay, then you can't see the questions. Okay, if you really can't see it, either move up or you can pull it up on your computer. But, oh, actually, maybe this would be better. Is that any bigger? Is it a little bit bigger? If I can zoom it in here. Oh, yeah, there we go. We'll do that. It's better, isn't it? Anybody need more time? Okay, get in groups of 2 or 3 again and talk about your answers. And I'm also gonna, this is a question straight from the MyLab assignment. So I'm also gonna kind of put up what it said on MyLab too, because obviously on D, you couldn't type out your answer. It'll be like a multiple choice. So that way you can just see how they're wording things. Okay. So go ahead and start checking with somebody, and in here we've got our answers. Actually, that's right. It's here too. Yeah. I think there's a there's for comparisons that really 3 years ago, most records are the same about 70%. Yeah. That's where I felt. Yeah. I'm understanding the math this time, and also it's kind of weird. Awesome. So have you liked all the stat stuff better so far? Or is just this lesson you're saying that about?
I mean, I'm pretty big in statistics for some reason.
A lot of times people who don't like the algebra kind of part of math, statistics is their thing. And sometimes geometry as well. It's kind of like the stats and geometry are just a little different.
I don't know. Awesome. So would you, but I can't do that, it's right. And then letters, the equation,
It's just like your, it's maybe your semester then.
Yeah, good so far.
Awesome. Okay, any questions about that one? All right. Oh, sorry, what'd you say, Caitlin? D doesn't? Okay, so first of all, men marry about 3 years later than women. That part probably makes sense because of what you had up here, right? Okay. The spread is about the same because when you look at the Q3 and Q1, and the Q3 and Q1, they're very close. That's kind of what you answered on, there we go, on part C anyway. And then about 75% of men marry later than 75% of women. That's just because, there we go. If you look right here, this is where they overlap, just this little spot right here. And so that's, they only have about 25% of those ages in common, and the rest are out of that range. Okay. So you didn't have to figure out the 75% because they told it for you, but you can see that it only overlaps a little bit there. Okay, next, an outlier. An outlier is a value that is widely separated from the rest of a group of data. So if we look at the scores, 91, 92, 92, 93, 93, 93, 94, all of that data are grouped very close together. There are no values that are widely separated. However, if you look at the tests, at the scores, 21, 92, 92, so on, all the way up to 150, when you look at those scores, the 21 and the 150 are widely separated from the rest of the data. So those two numbers are potential outliers. So if it's officially called an outlier, then an outlier is any value that is more than 1.5 times the interquartile range above the upper quartile or the Q3 or below the Q1. Outliers are commonly indicated with an asterisk. And then when you draw your whiskers, you're going to draw them to the minimum and maximums that are not outliers. So let's look at an example of how to see if you have an outlier with some data. So here, this table shows the final medal standings for the top 20 countries in the Summer Olympics. We want to draw a box plot of the data and identify possible outliers. So when we look at this data, our extreme scores look like maybe 110 and possibly the 11. Okay, I'm thinking probably not on the 11 to see how close it is to the next number and so on. But we can use our little 1.5 times rule to figure that out. Okay, so if I want to find my important values for my box plot, we're not going to worry about the minimum and maximum yet, because if we have an outlier, that's going to change that. Okay, so let's go ahead and find the median. We have 20 countries, so that means I'm going to have an even number of data points. So I want to count out 10 and look at the 10 and 11, which would be 27 and 25, and find that average. So what is my median? If 27 and 25 are the middle points, what's the median? 26. Okay, so the median is going to be 26. When I want to find Q1, this is my cutoff point here at Ukraine at 27. I want to find the middle number again. Well, we're still dealing with 10 and 10. So if we want to find the middle of 10, I need to go 1, 2, 3, 4, 5. And I want to look between Germany and Australia. So 46 and 41. If I average those, that's going to be a half, thinking 43.5. Does that sound right? Okay. And then let's see, count 1, 2, 3, 4, 5 here. And 18 and 16, what's the middle of those? That one's a little easier to figure out in your head. That's going to make 17. So that's going to give me my median is 26, my Q1 is 17, my Q3 is 43.5. Now, how do we find the IQR? Subtract Q3 minus Q1. So if you take 43.5 minus 17, you end up with 26.5. So our rule said if we're going to figure out whether these extreme scores are officially outliers, I'm going to take the 26.5 and multiply that by half and add it to my 43.5, subtract it from the 17. So outliers are anything that is greater than 43.5 plus 1.5 times 26.5. When you put that in your calculator, you should get 83.25. Okay, and then take 17 minus the 1.5 times 26.5, that gives you negative 22.75. So anything greater than 43 or 83.25 is an outlier. Anything less than negative 22.75 is an outlier. Do we have any outliers? Yeah. The 110 is an outlier, but not the 11. Okay. And then I think we actually have another one too, don't we? Under 100, yeah. So both of these are going to be outliers, the 110 and the 100. That makes sense? Okay, so that means when you draw your box and whiskers, you're going to make the whiskers go to the 11 and to the 70, what was that one? 72. And then we're going to put asterisks on our outliers. were 100 and 110. Any questions there? We okay with outliers? Okay, box plots are used primarily for large sets of data or for comparing several distributions. But the stem and leaf plot that we talked about last week, it's usually a much clearer display for a single distribution. Sometimes parallel box plots drawn using the same number line will give us the easiest comparison of medians, extreme scores, and the quartiles for the sets of data. So we kind of saw that on that marriage problem that we did earlier. Those were that was an example of some parallel box plots. You could easily see when you're comparing men and women, you could easily see what was going on because those are right next to each other. Although we cannot spot clusters or gaps in a box plot, we can with stem and leaf or line plots. And the line plots are what y'all are gonna watch the video on. So you'll, I feel like that section was all about line plots and scatter plots, which we talked about that a little bit last semester for those of you at 205. And then you also talked about those if you took college algebra. Okay. So that's why I thought that would be a better lesson for you to kind of do on your own. I feel like you're probably going to be a little more familiar with that. With box plots, we do not need to have sets of data that are approximately the same size as we did for stem and leaf plots. And then to compare data from 2 or more sets using their box plots, you're first going to study the boxes to see if they are located in approximately the same places. And then you're going to consider the lengths of the boxes to see if the variability of the data is about the same. And then finally, you're going to check whether the median, the quartiles, and the extreme values in one set are greater than those in another. Okay, so there will be a set of problems where on your assignment where you're maybe asked to say, okay, which would be a better type of graph to make? And so these slides here would help you with that. And there's also a set of slides in 10.3 when you all watch that video lesson that talks about when to do the different types of graphs. Okay. Okay, I feel like we did one like this with our trial problem. So we're gonna save a little bit of time here and skip over this one and move on to variation. Okay, with variation, we're gonna look at something called mean absolute deviation. We're also gonna look at variance and then standard deviation. So a measure of spread is needed when data are summarized with a single number, such as the mean or median. Okay, the simplest way is to find the range. We can also use the interquartile range, the IQR that we talked about earlier. And then we also have a more sophisticated way called the standard deviation. So we saw early in this lesson, we saw 2 sets of data where they both had the same mean. I think that was like 5, but one set of numbers were all clustered together. And then do you remember the other set of numbers where it went from like a negative all the way up to 20, but yet they had the same mean? Well, you wouldn't know, the difference necessarily if you were just describing the data about mean. So in something like that, it's helpful to have an idea of the spread of the data, so you know how what the range of numbers are. So range and IQR are pretty easy to find, but then the standard deviation is a more sophisticated way, and you'll see that a lot, like as you all become teachers and you'll find out pretty quickly there's a big push on all the test scores and where your students stand on their MAP scores and official state assessments and all that. And so I wanted to make sure we at least talk about standard deviation so that you'll know what that means, because that is in a lot of that data. Okay, the mean absolute deviation, which we'll abbreviate as MAD, so we don't have to write that out. That makes use of the absolute value to find the distance of each data point away from the mean. Then the mean of those distances is found to give an average distance from the mean for each of the points. So when you want to compute the MAD of n numbers, here are the steps. You're going to measure the distance from the mean by subtracting the data value minus the mean. Then you're going to find the absolute value of each difference. You'll add all of those values and then divide by the number of scores. Now, if you like to see this kind of written as a formula more so than out in words as steps, this is what the formula would look like. Okay, this absolute value part just means that you don't want to have any negatives. Okay, remember absolute value makes it a positive. So when you're finding that distance would always be positive. Okay, so let's look at a table to see how to find those values. Okay, so we have test scores of 99, 67, 84, 99, and 67. So we have 5 test scores here. If we need to find the mean of those test scores, we're going to add those 5 scores up and divide by 5. My division bar is gone there. I don't really know what happened, but pretend like division bar there. That would give us an average of 83.2. So now to find the mean absolute deviation, you're going to go through and say, okay, how far away from my mean is 99? So 99 minus 83.2 is 15.8. Then you do that for the next test score. Okay, this one is on the other side of 83.2 though, so we don't want to have a negative. Okay, that's why we're taking the absolute value. That's the distance of 16.2. The 84 is really close to 83, so that's just a difference of 0.8. And then from 99, that's a difference of 15.8. And then finally, 67 is a difference of 16.2. Okay, then I add all of these numbers together, all those differences, to get a total of 64.8. And we have 5 test scores, so I divide by 5. That makes my MAD 12.96. Questions on how to calculate that? Okay, so here's what this looks like on a graph. You can kind of see what it means when you look at this bar graph. This is marking my mean, and here is my mean. And you can see all of these are, this side is the same distance away as this side. Okay, the variance and standard deviation are 2 commonly used statements of dispersion. These measures are also based on how far the scores are from the mean. So here's how we will calculate the variance of n numbers. First of all, we're going to find the mean of the numbers. Then we're going to subtract the mean from each number. So steps 1 and 2 sound familiar, don't they? Here's where it gets different. With variance, after you find those differences, you're going to square each difference. Then after you square each difference, you'll add those squares up. And divide that sum in step 4 by the number of data points you have. And then once you've done that division, you'll find the square root to find what's called the standard deviation. Okay, so step 5 gives you the variance, and then the standard deviation is just the square root of the variance. Okay, so these are the steps written out in words. For those of you who like formulas more, this is what the formula would be. S stands for standard deviation. It's just the square root of the variance. And then this is your formula for that. You're going to, this is where you're subtracting the difference between the value in each of the means. You square them, add them all together, and do a big square root there. Now, those of you who have TI 83 or 84, you can put this all in your calculator in one step using your fraction button and just put a big square root around it. If you think that will be confusing, it might help to write out each step in like a table and go from there. Okay, let's look at an example. Professor Abel gave 2 group exams. Exam A had grades of 3 zeros and 3 100s. Exam B had grades of all 50s. We want to find the following for each exam: the mean, the range, and the mean absolute deviation, and then we're going to go on to find the variance and standard deviation. Okay, so how would we find the mean? Add and divide by what? So in this case, we have 6 in each set, right? Now, this you shouldn't, if you can see the pattern here, you really don't have to do a whole lot of calculating, because if you have 3 zeros and 3 100s, what's your average going to be? 50. Okay, and then if you have all 50s, what's your average going to be? 50. Okay. So really what they're wanting you to see here is you have 2 exams with the exact same average, but if you actually look at those scores, they're nothing alike, are they? Okay. So that's why these measures of variation are so important. Okay, when you look at the range, you can start to see it, because what's the range of exam A? So your range would be 100 because you're subtracting those 2 values, whereas your range on exam B is what? Not a range, is there? It's just 0 because everybody made the same score. Okay, then for your mean absolute deviation, for exam A, that's going to be 50, and for exam B, that's going to be 0. And that's just because there was no deviation from the mean here. It was the same. That's what we had there. And then for exam A, since this is literally in the middle of all the data points, we didn't have a lot of different values there. That one, we didn't really have to use the formula so much to figure that out. Okay, standard deviation is our big square root formula. So for exam A, and I just put a little A here so that you would know this is how to find the standard deviation for that first set of data points. Since we had 3 scores that were 50s and 3 scores that were 100s, I could kind of combine this, and instead of writing 0 minus 50 squared 3 times, I just did 3 times that. And the same thing for the hundreds. So we have to take 100 minus 50 3 times. I just put the times 3 here, so I wouldn't have to write this out plus 3 times. Now, do we want to take a second to make sure you can put that in your calculator, okay? I feel like we probably should. Okay, if you have a TI 84, you can go to get your square root button. That is at the X squared button, diagonal from 7. You can see it there in blue. So if I hit the blue key and then X squared, it brings up my square root. Okay. So blue key and then X squared, diagonal from 7. Then if I'm just going to type in this first line. If you have an 84, the easiest thing to do would be to say alpha y equals and bring up your fraction button and type in 3 and then make this bigger so you can see what I'm typing in. And then hit your squared button and then plus 3 times 100 minus 50 and hit your squared button. We're going to do that over 6. That gives you 50. Now, if you have a TI 83, you do not have the fraction button. So what you need to do is when you hit your square root button, you're going to put parentheses around the numerator. And then once you're finished with your numerator, before you hit divided by 6, you'll close that and then hit divided by 6. Just make sure that's still underneath the square root. You can see how it is here as well. And then when you hit enter, you'll still get 50.
Mine doesn't show the line, it just says like it's,
Like this.
yeah, mine doesn't have a line, it just says the beginning and then I type it all out. And
Did you hit the divided by?
yeah. I think I have to type it.
Oh, I see what you're talking about. The big, it's not showing it.
Yeah, I have it.
Okay, so the reason is
Because we.
did yours do the same thing? Okay, you're gonna need one more set of parentheses because it thinks that the divided by 6 isn't under the parentheses. So if I can. See that extra parentheses up in there and after the 6? It shows all of that's under the rounded. Yes. Okay. Okay, when you find the standard deviation for set B, that is the one where everyone made a 50. So we had 6 people that made a 50. So I just did 6 times that. 50, 6 times, okay? And then your standard deviation would be 0 there. Okay, the median is going to be 50 for both because that would be your middle number averaged. And then the interquartile range really tells you what's going on here because For exam A, that's 100, and for exam B, that's 0. Okay, then next we have something called normal distributions. The graphs of normal distributions are the bell-shaped curves called normal curves. So if you've ever asked, are you grading this on a curve? Typically, if it's a true curve, then what the instructor does is they make their data fit into what's called a normal curve. The normal curve is a smooth bell-shaped curve that depicts frequency values distributed symmetrically about the mean. So most of the time we typically think, oh, are you going to curve this? And you're thinking they're just going to add 10 points to everybody's grade. And sometimes that is the case, but if it's following a true bell curve, then that means that all of the data is distributed symmetrically about the mean. The mean, median, and mode all have the same value. The curve extends indefinitely in both directions, and it gets closer and closer to the x-axis, but it never touches it. And the curve is symmetrical about its center point, but not all symmetrical distributions are normal. Now, here's what the normal curve looks like and how the data is distributed. And when I work through these problems, I like to have that in front of me. So I made a copy for all of you so you can kind of see how it works. And when you answer questions about this, you can refer to that slide or this paper. Okay, so do you see the line that's going right down the middle between the 34%? Can you tell what that says at the bottom of that line? Do you see the X bar? What does X bar stand for? That's your mean, okay? And then your mean is right in the middle. And then all of your data points, like these other lines, represent a standard deviation from the mean. One more. This would be this line between the 2.4 and the 13.5 would be 2 standard deviations from the mean. And then 3 standard deviations from the mean. I keep touching that and making it go back. So on. So 68% of your data will fall in the middle. 95% of your data fall within 2 standard deviations, and 99.8% of the data falls between 3 standard deviations of the mean. So those percentages on the graph represent approximations of the total percent of area under the curve. So here's how this works. When a standardized test was scored, there was a mean of 500 and a standard deviation of 100. It says, suppose that 10,000 students took the test and their scores had a bell-shaped distribution, making it possible to use a normal curve to approximate the distribution. How many scored between 400 and 600? Okay, so here's what you need to pay attention to, and I really wish I could get this pen to work. I was planning on using that to write with, but that's okay. We'll figure this out. So we have our mean of 500 and our standard deviation of 100. So what that means is that here, you're going to put, work here? No, you would put 500 at the X bar. Now, if our standard deviation is 100, then that means if this is 500, my next bar is going to be 600. What's the next one? 700, and then 800, okay? Because in this case, since your standard deviation is 100, every line represents another 100. So if I'm going in the other direction, if this is 500, what's this line before it? 400, before that, 300, 200. Okay, so this question is saying, how many scored between 400 and 600? Well, the 400 and 600 are right here, right? So what percentage of people are in that range from 4 to 600? See, we're at 68%. You're between those two numbers, 68%. So 68% of the people scored in that 4 to 600 range. Okay. So what you're going to do is take 68% times 10,000 because that's how many students took the test. 0.68 times 10,000 is 6,800 students scored between 4 and 600. Draw this here. So this was my 500. This was 600, 700. This was 400, 300. So everybody see how I figured out what those lines were? If this had told me that the mean was 20, I'd put a 20 there. And if my standard deviation was 5, then I would say 25, 30, I'd come back here and say 15, 10, so on. So every time you have a new problem, your median goes here, or sorry, the mean. And then the difference from here to here should be 1 standard deviation. That should be 1 standard deviation. So this next problem part says how many score between 300 and 700. So there's 300, there's 700. What percentage does it say on your chart from there to there? 90 what? 95? So if 95% of the people scored that between 3 and 700, then you're going to say 0.95 times 10,000, which gives you 9,500 scored between 300 and 700. Okay, and then how many scored between 200 and 800? That was the 90, what was it, 99.8? So you're going to say 0.998 times 10,000, which is 9,980 students scored between 2 and 800. Okay, how many scored above 800? Yeah. Okay. So you only have 0.2 left on each side, but if you want just this side, that's going to be 0.1. Okay, and it's actually 0.1%, so you're not multiplying by 0.1, you're multiplying by what? 0.001. So only 10 students scored above 800. Okay, so suppose that a group of 200 students asked their teacher to grade on a curve. If the mean of the test was a 71 with a standard deviation of 7, then this is how you would make your new graph. This is 71, your next line would be 78, and then 85. Going the other way, it would be 64, 57, so on. And then here's your A, B, C, D, and F. So 68% of the people should be making a C. 13.5% of people make a B. Only 2.5% of people make an A. So I actually, in high school, had a physics teacher that literally graded every test on a curve, on a bell curve, on a normal curve. So, and I am, like, you're supposed to be good at science if you're good at math. I'm not good at science, I'm good at math. And I mean, I would study, and I finally got like a passing, what, you know, numerically was a passing grade on a test. I think I got like a C, and it ended up being a D or an F because even though numerically my score was like 70 something, since so many others in my class had done better when he put the data in here. I actually fell over in here still. It was crazy. So, yeah, be careful asking a teacher to grade on a curve, because this is supposed to be grading on a curve, but this is the actual curve. It doesn't automatically mean that you're adding points to everyone's grade. Okay. So that's what it would look like. All right, so we're kind of running out of time, but I wanted you to at least see percentiles. This was not something we have to cover, but I wanted to at least touch on it because do you remember as a student getting like scores back or being told during whatever percentile? So did you know what that means? ACT scores a lot of times are recorded in percentiles. A percentile shows a person's score relative to other scores. Percentiles divide the data into 100 equal parts. Deciles score divided into 10 equal parts. You don't see deciles as much as percentiles, but I wanted to make sure we went over that. The R's percentile is represented as P with a little subscript there. Okay, a standardized test that was distributed along a normal curve had a median and mean of 500 and a standard deviation of 100, so similar to what we have here. The 16th percentile is 400 because 400 is one standard deviation below the median. So 50% of the distribution is less than 500. So basically anybody who made a score of 500 on this test would be in the 50th percentile because that's where the middle is. All right, and I know we're out of time, but I only put one problem about percentiles. So if you need to go back and look at examples 14 or 15, that should be the last couple of slides there. I don't want to keep you and make you late for your next class. I told you all this is a long one. So we're counting the trial problems as your group grade for the day, since we didn't have time to do everything in groups. So we're just counting that there. Once again, next week we'll be reviewing and taking our test. So when I see you all in class next week, it'll just be a review day. So bring some earbuds in case you want to listen to music while you're working. I know some people prefer to do that. That also means any work from Unit 1, you're going to need to make sure you have done by next week or it's closed forever. Yes, question.
So the test will be next